Hi, so welcome back. So let's continue with our discussion. In the last session, we have defined something called stalks of sheaves. So this basically holds the local properties of sheaves. So if you want to study some local properties of a sheaf, it is enough to study those properties in terms of the stalks at every particular point. And you know that if you change the element like P and Q, Fp and F of Q, this may not be same, okay, but both will be abelian group, and you are most familiar to work with abelian groups. And we have also given you an exercise to try to meet this theorem that the isomorphism of two sheaves on a same topological space X is equivalent to the isomorphism between the stalks at every point of this topological space. So if you have tried it, then it's very good, but if anyone is not capable to do it, so let me give you a brief overview of the proof. So for example, suppose phi from F to G, this is isomorphism of sheaves. So how can I construct phi p from Fp to Gp such that phi p of u comma s is defined as u comma phi u of s. Note that phi from u to F to G, there is a map, so of course there is a group homomorphism from Fu to G of u. Okay, so this is so group homomorphism of abelian groups. And if you have S here, so you can have u of S here. So of course this map makes sense. Now to check that what is the inverse of this. So as it is phi from F to G's inverse is isomorphism, so there is a mapping from G which is from G to F such that she composed phi is identity over F and phi composed she is identity over G. Alright, now okay, so let's just try to figure out what is the stalk. So just that stalks of composition morphism. So you know, right, that Fu to Gu, suppose Hu, there is map phi1 u, here it is phi2 of u, and here I have f of v to g of v to h of v. So here to here, here to here. So let's say it is rho uv, it is theta uv, it is rho dash, and here it is phi1 of v, it is phi2 of v, and from here to here is the composition of these two maps, that is phi2 composed phi1 of v, something but phi2 of v composed with phi1 of v, and from f of u to h of v there is map phi2 composed phi1 of u is nothing but phi2 of u composed with phi1 of u. Alright. Now from f of u to f of p there are maps, right? From g of u to g of p there are maps. Okay, and from h of u to h of phi there are maps hp. Alright, now you see one thing, that from fu to gu you have phi of u, and also from here to here you have g of u. Now what is the property of morphism into sheaves? The property says that this diagram should commute, this particular diagram here to here and here to here, this diagram should commute. So as this diagram commutes, and of course also this diagram should commute, right? Now this, think about this particular composition map. So I mean, you see that, for example, just move it like this. So let not write like this, so just write it like this. So we have GP like this here. Okay, so this diagram and this diagram commutes, right? Again this one and this one, so this diagram commutes. Now if you consider this composition of these two diagrams, this one, consider this composition map, consider this composition map. That means then as both the subparts of this entire pentagonal diagram commutes, so then the entire pentagon must commute. That means this one and this one, this must commute. Okay, of course you just take it this like this, take it like this. So as these two commutes, so by property of direct limit there must be a map from FP to GP. Okay, similarly I will get a map from GP to HP. Now if I do the composition of these two maps, GP to HP and FP to GP and GP to HP, then there is also always, so let me just write it. So how the map will be defined? So the map is basically defined like this. So from FP to GP there is a map, let us call it as phi1p, and from GP to HP there is a map called phi2p. So how this map is defined? This map is basically defined such that this particular diagram, this one and this one, this diagram commutes, and this one and this one, this diagram commutes. Similarly, how this map is defined? This map is defined such that this one and this one, this diagram commutes, and this one and this one, this diagram commutes. Okay, So that means both the diagram satisfies the universal property and all the others one related to the direct limit system. So if we glue these two maps phi1p and phi2p, the composition of phi1 and phi2p, let's say phi2p composed with phi1p, this also satisfies the universal property. So as this satisfies the universal property and the maps are basically constructed in this way, the maps between the stalks are constructed in just satisfying the universal property, then of course this should be phi2 composed phi1. So by the construction, how it is constructed, how the construction happens. So the construction I have mentioned just with respect to phi p to gp. Okay. So that means, so here I should get that she composed phi of p is nothing but fp. Identity f, stalk of the identity map is nothing but fp. I mean not identity fp, it is identity over fp. Over fp. So it is she p composed with phi p is identity over fp. Similarly, phi p composed with she p, it is identity over g of p. So as it is these two maps are identity maps, so that means phi p, this has both sided inverse. So as it has both sided inverse, that means phi p, this is surjective. Okay, and the converse one is also the converse one is much straightforward. That suppose phi p from fp to gp, this is isomorphism. So we define, so I mean then we'll define that phi u from fu to gu is isomorphism. So if it is isomorphism, then it is enough to work with all those just in terms of phi, right? So let us take any u from here, and phi u of is basically is defined as just, I mean, okay, I mean not used like this. So it is so yeah. So for example, let us consider that phi u of s1 is same as phi u of s2. So as both are same, so u comma s1, phi p of u comma s1 should be same as phi p of u comma s2, right? So then of course u comma s1 is same as u comma s2. So there exists Vp that contains P, and so the S1 restricted at Vp is same as S2 restricted at Vp. Okay. So S1 minus S2 Vp, it is 0. So I mean P is an element, so that P belongs to U. So I will just let P to be varied over entire U. Then I can write U to be as a union or of Vp, such that P belongs to U, such that it is an open cover, and S1 minus S2, it is this Vp is 0 for every p. So that means S1 equals to S2 by the property of sheaves, right? So that means it is injective. Okay, so phi u is injective. So again, so phi is injective. Again, surjectivity is also just following the gluing lemma, gluing property. So that means I take any small t belongs to g of u, then as small t belongs to g of u, now so u comma t, this belongs to g of p. You take any small p belongs to u, okay, then there exists small s belongs to f of u such that phi p of u comma s is equals u comma t. So that means u comma phi u of s is equals u comma t. That means there exists Vp contains p and Vp is inside u such that phi of u of s minus t restricted at Vp, this is 0. Now we let p to be again run over entire u, so I can write u as union of Vp so that p belongs to u, and I will get phi of u of s minus t over Vp is 0. That means phi u of s minus t is 0. Okay, so this is how one can define the, I mean, this is how one can show that phi u, this is surjective. So now, I mean, the proof is not, I mean, for now it is easy, it is easy, so that means phi u is bijective. Bijective, so there exists she from gu to f of u such that phi u of inverse is she u. Then phi inverse is nothing but she. This works, this will work. By the way, so let me just make a small note that suppose phi from F2G is a morphism. Now if each phi of u is isomorphism of abelian groups from f of u to g of u, then phi is also an isomorphism. In fact, it is easy to check that for every u I will take she u, just what I have just said here. I will take she u and I will show that phi inverse nothing but she, and collect all those she u's, and I will construct she as well. But what about the converse? So the answer is may not be true as well. So your exercise is to find counter exam. If you can't find it, let us keep it for the next session. I want you to try it by your own once, then we will discuss it in the class. Anyway, so now just go back to the basic ring structure, basic ring and module theory. So suppose phi from A to B is a module ring homomorphism. Okay, then we could talk about kernel phi. We could talk about image of phi. We could talk about co-kernel of phi. So similarly here as well, suppose phi from F to G this is a sheaf of it is a morphism between two sheaves. Morphism between sheaves. So as there is a morphism between sheaves, we can talk about the kernel phi. That means kernel phi, this is said to be presheaf kernel. You can talk about co-kernel of phi. This is presheaf co-kernel, and we can talk about image of phi. This is said to be presheaf image. Presheaf image. So how the presheaf kernel is defined? So it is U is mapped to kernel of U, and whenever U is subset of V, in that case I have phi U which is from FU to GU, and let's say it is FV to GV. So here I have kernel of phi U. I can restrict it as if a kernel of phi of B as well. So that means I can just take VU. So okay, let me define it later in the next page. So here it is, U is mapped to co-kernel of phi of U. So co-kernel of phi of U means G of U quotiented by image of phi of U. And what is presheaf image? Mapped to image of U. So let us see how the restriction maps works here. So for example, let us consider FU to GU, GV, it is rho UV, it is rho dash UV, so it is PU, it is phi V. So I can take, let's say, kernel of U I am taking as small x belongs to kernel of U. So if I take x restricted at V, what happens to x restricted? So phi U of x, this is 0. So phi U of x restricted at v, this is also 0, because under group homomorphism 0 mapping to 0. So what does this mean? So it is phi of v, x restricted at v, this is 0. That means x restricted at v, this belongs to kernel of phi of v. So the usual restriction maps works. So here usual restriction maps. Alright, again here also, so how the elements should looks like here. So this should look like let's say for example, I take small t belongs to g of u. Okay, now I take u is subset of v, so small t belongs to g of u. So what about t restricted at v? I obtain it here, t restricted at v. Okay, then we can always talk about t restricted at v plus image of phi of, because image of phi of v is I mean is an ideal of g of v, right? Actually identity image of v, that's how we can define image of phi, image of a homomorphism. So here also usual restriction, and similarly here also you can find that it is usual restriction. Now the interesting fact is the following, that this kernel of phi, this is a sheaf, whereas this one and this one may not be sheaf. Okay, so it is also a very good example that when a presheaf is not a sheaf. So kernel of phi is always a sheaf. You can check by using by the properties of a sheaf as well, but these two may not be a sheaf. So we have so far discussed a lot of things, in fact a lot of presheafs where it is not a sheaf, and I promised you every time that I will define something called sheafification. So now it's very very urgent to know that how to obtain a sheaf structure from a presheaf. Okay, it has considered that f is a presheaf. Okay, so then how can I get some sheaf from here? So as it is a sheaf, so I can always talk about, so okay, what are the properties I have? So the properties, first of all, what I have is something that from u to f of u, this identification I have. Also I have rho uv from each fu to f of v, as well I have that suppose w is subset of v, subset of u, then I can define it as, let's say, rho uw is nothing but rho vw composed with rho uv, this composition map. Now to get it as sheaf, I just need two things. One is local property and to gluing. Okay. Now in order to add these two conditions, I need to do some changes. So there's a proposition. This says that suppose we have a f is a presheaf, then there exists a sheaf f plus and morphism, let's say theta, from f to f plus with the property that for any other sheaf, let's say G, okay, for if any other sheaf, let's say G, if there exists a morphism phi from F to G, then there exists a unique morphism of sheaves, let's say psi from F plus to G, such that phi equals she composed theta. So that means, let's say it is my f from f to f plus, there is a map. E from is any, somewhere there is a morphism of presheaves, then there is a morphism from here, that is she, let's say it is theta, it is phi, and this diagram should come out. Okay, so somewhere it is similar to the universal property, right? So this particular phi, sorry, f plus, this particular f plus, this is said to be sheaf associated to the presheaf, and this f plus is unique up to isomorphism. This f plus comma theta, this is unique up to isomorphism. So how this f plus is defined? So f plus, so definition, it is defined as for every u, f plus u is defined as, let's say, set of all S from U to disjoint union of FP to U, such that it is basically a set mapping, okay? Set map such that S of P, this belongs to F of P, and S is locally constant map. So what does mean locally constant map? Means for every small p belongs to U, there exists Vp containing P, and this is inside U, such that S restricted at Vp, means S of Q is a particular x naught for all Q belongs to Vp, and x naught is a fixed element. fixed element. Means I can also as well write it as t comma, let's say vp, and t is fixed element or fixed section. Okay, so this is how I can define. So I mean this one is actually amplification of this. Okay, right. So this is how we can define the, that means once you have a presheaf and you get a sheaf from that presheaf, you are just considering the section as some set mappings, okay, which is locally constant map. Right, so this A plus is said to be sheaf obtained by sheafification. Okay, so whatever presheaf I have, if it is a sheaf, then after sheafification I will get the same sheaf, because in that case this S will be nothing but identity ones. Okay, in fact in that case it will be nothing but identity 1 and F nothing but F. You can consider anything as like this, not this one identity, I'm sorry, this one identity. Means suppose F is a sheaf, for example, suppose F is a sheaf. Okay, so if F is a sheaf, in that case I can define A plus of U a set of all small s belongs to U2 disjoint union AP such that S is constant. It is constant everywhere, so of course it is constant at every point. So that means I will take, let's say, S of p equal to x naught x, this one, so it is one function. Again I will take another function S of p with some another element section like this. So in that case A plus is nothing but F and theta the identity one, and it is unique as you have F to be fixed. But if it is not a presheaf, not a sheaf, in that case we have to sheafify these things. Okay? In algebraic geometry, whenever I consider, mostly in sheaf of modules or formal schemes, whenever I will consider any presheaf and later I will say that it is working as a sheaf, means I am sheafifying that thing. Okay, so sheafification more or less does not change the open sets. Actually this basically takes care of the gluing property and local one to make it a sheaf. So let me give you a small exercise that sheafify the constant presheaf. Okay, sheafify the constant presheaf. Right. So now let me give some more implication on kernal sheaves and sheaves. So suppose I have phi from, let's say, F to G. This is a morphism between sheaves, right? I have already said that it is isomorphism if and only if phi p is isomorphism. but this may not imply that phi u is isomorphism for every u. In fact, it is for every p belongs to x, it is for every u is subset of x. It may not be true. So the question matters at where the problem happens. Let's verify. So suppose that phi from f to g, this is, suppose it is injective. So as it is injective, so let us consider phi u. From fu to gu, okay? So now phi is injective. Okay, so first then what can we define by phi p of ap to gp, right? Now phi is injective means what? So phi is injective means okay, let's go by step by step. So phi is injective means what? If we consider, let's say, kernel of phi, okay, what is kernel of phi? Phi is said to be injective if the kernel of phi, this is 0, okay? So means kernel of phi is 0, means it is basically a zero sheaf. And suppose that if kernel of phi is 0, okay, it is in kernel. In fact, it's economic condition that, like, you have phi from a to b is a ring morphism. So a is, if is injective, if and only the kernel is 0, or a trivial one. So here also the same thing. It's a constant sheaf. It's a constant zero sheaf. Now suppose we have that, so kernel of phi is 0. So what about kernel phi of p? So kernel phi of p means the stalk of concrete. So the element should look like u comma s, where S belongs to kernel phi of u, right, for every u. So S belongs to kernel phi of u means phi of u of S, this is 0. So that means if you consider that phi p from fp to gp is the induced group homomorphism, in that case phi p of u comma s is nothing but u comma phi of s, which is nothing but u comma 0, of course 0. That means u comma s, this belongs to kernel phi p, okay? Now again let u comma s1, this belongs to kernel phi p. In that case u comma phi u of s1, this is 0. So phi u of s1 restricted at p, at vp, it is 0. And then I can vary p for every, it is for every p. For every small p belongs to capital U, there exists Vp subset of U and P belongs to Vp. So I can vary this over entire P, then I will get that phi U of S1, this is itself 0. So as it is itself 0, so that means S1 belongs to kernel phi of u. Okay, so S belongs to kernel phi of u means what? U comma S1, this belongs to kernel stalk of this kernel phi. So that means what actually I have got, that the stalk of kernel phi of p is same as kernel phi p. Okay, now if we now get back to our own condition, that if we have injective map, then kernel of phi is 0. So that means kernel phi of p, this is 0. So this is strip and only if at every p, this is strip and only if kernel phi p, this is 0. Right? So we already, that means phi is injective if and only if phi p from fp to gp is injective for every p belongs to x. Okay, right. Now what about, now what is the picture in open set level? So phi u is from fu to gu. So let's say small s belongs to kernel phi of u. So that means u comma s, this belongs to kernel phi of p. So that means it is 0 for every p belongs to u. So that means u comma s is 0. So there exists vp subset of u and p belongs to vp such that s restricted at vp, this is 0. So that means then I can vary p over the entire u, and I can cover u with all such vp's, then I will get that s is 0 itself. So that means kernel of phi u, kernel of phi u, this is 0. So phi u is injective. But so injectivity, so phi is injective, that means it is injective in the stalk level, that means it is injective in stalk level as well as it is injective at open set level. Now what about the converse one? Converse one means, suppose phi from f to g, this is injective at stalk level. That means phi p from fp to gp is injective for every p. So that means kernel of phi of p, phi p, this is 0 for every p. So that means the stalk of sheaf of kernels, this is 0. So kernel phi is always 0. Okay, so stalk level implies global level. Let me just write it for now, global level. It may not be, it is not a clean one. In fact, it is clear from this one, that it's clear from this that phi is injective and phi p is injective. So phi p is injective means is also injective. So in fact, injectivity at stalk level if and only if injective as a whole. But what about the converse one? For example, suppose open set level it is true. So phi u from fu to gu is injective. Okay. So kernel of phi of u is always 0. Now if you want to define that the kernel of phi is 0, so let u comma s belongs to kernel phi of phi p, kernel of phi p. So phi p of u comma is nothing but u comma phi u of s, this is 0. So u comma s wait for that done. So phi of u is 0. So okay, phi p oh sorry I'm sorry I don't know that. Okay, so yeah, so let p belongs to u be any point, and it is open for every open set phi is injective I have, yes. So now that means let's say it is there, so s must belongs to kernel of phi of u, that means s has to be 0. So it is u comma 0 is nothing but 0. So that means phi p is injective. As phi p is injective means phi is injective as well. So that means open set level, if and only if stalk level, if and only if as a whole, both are actually equivalent to each other, and it is true for injectivity. Now let us see the same one, is it true for surjectivity? So similarly to the similarly like kernel phi, you can get that the stalk of image sheaf is nothing but image of phi p. And once I have phi from f to g, this is surjective. It is surjective means basically definition says that image phi has to be g. So image of phi means what? It is image of phi p. This has to be gp, right? So it is true if and only if this is true. So that means what? Phi is surjective if and only if phi p from fp to gp is surjective. Again, suppose we have phi from f to g, this is surjective. So who can tell me that fu to gu, this is surjective? Let us verify is it possible or not. So for example, let's consider t belongs to g of u. So t belongs to g of u. So phi surjective means phi p is surjective. So that means u comma t, this has a pre-image. So u comma t, this belongs to gp basically. So this must have a pre-image. So let's consider that u comma phi of u of s, let's say u not is, let's say is nothing but, okay, let's say not u, let's say v comma phi of v of s is nothing but u comma t. It may possible, right? Because nobody can tell me surely that okay, this has to be u. Can anyone tell me for sure like this? because I just know that T belongs to G of U, and it may be that there exists some W subset of intersection V such that phi of V of S minus T restricted at entire W, this is 0. Nobody can force me that okay, this has to be U is itself. Okay, so that means this might change. So I cannot take any way, cannot get back U every time, may not get back to U every time. So it means at open set level it may not be surjective, but the converse may be true always. For example, suppose phi U, oh, not here, let us write. Suppose from phi U I have Fu to Gu, this is surjective, and anyway, so let us take U comma T1, this belongs to GP. So that means T1 belongs to G of U. Now I can say that there exists small s belongs to F of U such that phi U of S is nothing but T1. Then I can write U comma phi U of S is nothing but U comma T1. Okay, then I can, for every S small p, I can restrict at certain suitable neighborhood and then cover entire U. Then I can get that phi U of S is itself T1. That means phi P is surjective. Phi surjective means phi surjective. So the moral of the story is the following, that when injectivity is there, in that case there is a triangular shape that as whole injectivity as a whole morphism of the as a whole, and at the stalk levels and at the open set level, both are equivalent to each other. Okay, but once the picture comes in surjectivity case, in that case surjectivity as a whole is equivalent to surjectivity at the stalk level, but this may not be surjectivity as open set level. This direction is not there, this direction is not there, but the converse is not always there. Okay, but open set level implies stalk level. Okay, all right, so let's stop it here. Hope you will try this exercise that the exercise that I have given you, that to sheafify the constant presheaf. This one is exercise, please note it down. We'll try this exercise, and in the next class we will study some more sheafification procedure, or some more sheaf obtained by sheafification of some other presheafs. Okay, thank you for you.